In the introductory module for this paper, I introduced you to the kind of problems we would address in this new regression paper. In this module, I'm going to introduce you to the kinds of data sets which we will cover and for which we will develop some methodology, and give you a brief motivation of why we would need to develop extra methodology for these kinds of data. In the regression modules which you have covered earlier, the methods have always been for continuous data. So because we have a continuous outcome, we have been able to assume normality, and based upon this normality, we have been able to develop inferential tools such as tests and confidence intervals. Now, strictly speaking, the properties of least squares estimators are valid even when we do not assume normality, but for the least squares methods and for the vector space concepts which we have used, nowhere have we assumed any restrictions due to the discrete nature of the outcomes. So let me provide you with an introduction to the kinds of data and why it is sometimes necessary to go outside the realm of the usual linear model to address these kinds of data. In regression 3, we will primarily develop methods for discrete data. So to repeat, the data which we have considered earlier is continuous. We have used the continuity of the outcome when we have assumed normality and developed inferential procedures under the assumption of normality. Now, as I said, strictly speaking, normality is not required, and the properties of the least squares estimators will hold in large samples even if the outcome is not normal. But generally, we have used least squares theory and estimation procedures where we have not placed any restrictions due to the nature of the outcome. Let me first provide you with an overview of discrete data. You have already had prior exposure to discrete data in the form of dummy variables. So when we have a categorical variable, a way to code it in a regression model is to introduce a dummy for each level of the category, and of course if we have an intercept in the regression model, then there will be one less dummy than there are categories. Now we have used such dummy variables as covariates in regression models. The most common regression models which have such covariates are the ANOVA model, where dummy variables are used to code the different levels of a factor, and ANCOVA models, which allow for the inclusion of dummy variables as well as the inclusion of certain continuous covariates. We see a piece of R code here, contra.treatment, and you will be familiar with this R code having seen it previously in ANOVA models to estimate treatment contrasts. So far, this has been your prior exposure to the concept of categorical and dummy variables. We are slightly going to change gears now to the case where the outcome is going to be discrete. We have two primary objectives in this paper. The first is to measure summary measures for discrete data. Now, if the outcome were continuous, you are familiar that R, for example, provides a 5-point summary of the data. So we can look at the mean, for example, the median, the mode, the standard deviation. We can look at the correlation when we try to see how much two variables are related. For many reasons, these are not natural measures to use when we have discrete data. So our first objective will be to try and get summary measures either for a single variable, for the bivariate case, and for the multivariate case. The second is to extend the concept of regression to a broader framework. I repeat that we have already used categorical variables in regression, but we have used them as independent variables or covariates. The inclusion of such variables has not posed any problems, and the linear model theory continues to hold regardless of whether the covariates are discrete or continuous. However, in this case, our outcome variable is going to be discrete, and as we shall see in the subsequent modules, this poses many challenges to the techniques of regression, and it is necessary to develop a broader concept of regression which allows for discrete as well as continuous outcomes. So these are the two primary objectives which we will address in this paper. A very famous dataset from R, in fact the faraway library in R, is the O-rings data. Now you may be familiar with the Challenger disaster in 1986. The Challenger space shuttle exploded a few minutes into its launch and killed all members of the crew on board. This was a major disaster and it led to a hiatus in NASA projects for many subsequent years. It turns out that a possible culprit could have been the O-rings. Now there are two boosters in the space shuttle, and in each booster there are 3 O-rings. It turns out that these O-rings had been tested at a temperature which was different from the temperature of the launch, and there had in fact been prior suspicion that the O-rings could fail at the time of launch and jeopardize the space shuttle. Now what I want you to notice from here is that our outcome is the probability of damage, or in the sample sense, the proportion of damaged O-rings. So the proportion of O-rings out of the 6 which are damaged. In this plot, which we shall revisit in subsequent modules, I have applied a linear model without going into any new methodological considerations. I have tried to model the probability of damage as a function of temperature and to see whether we could indeed have predicted the failure of the Challenger launch. Takeaway message from this slide is that the plot does not look too satisfactory, and one very alarming feature is that if we try and extend the temperature sufficiently backwards, we get an estimated probability which lies outside the range of 0 and 1. So I hope this provides you with some motivation for both the fact that we can have a discrete outcome for some data sets, in this case it is a proportion, and that if we apply the linear model in a blind fashion to this data set, the results will not be satisfactory. Here is another famous example from R. It is the baby food data set from the faraway library in R. So we are looking at 2 groups, boys and girls, and whether or not they have been fed with only the bottle, they have been given some breast milk with supplement, or they have been fed only breast milk. Again, the entries which you see in each cell are proportions. So this should provide you with a natural introduction to a case of categorical data. In this case, we have a 2 by 3 classification, that is, we have 2 variables, one of which has 2 categories and the third has 3 categories. In each cell, the entries are proportions as before. Whenever we collect data in an observational study, it is very rare that we collect data on only 2 variables. In any real-life phenomenon, there are always multiple variables which can affect the outcome, and in some subsequent module, we will briefly consider the idea of confounders and why it is necessary to control for them in our analysis. For now, confounders are a third variable which is independently associated both with x and with y. So in this case, our natural consideration for x is treatment, which can take 2 forms, A and B. Our natural consideration for y is the response, which could either be a success or a failure. My confounding variable is clinic. So the data has been collected from 2 clinics, which I have labeled as 1 and 2. The reason we are concerned about clinic is that it is possible that clinic is associated with treatment, in the sense that there may be more preference for a particular treatment in a particular clinic, and clinic may or may not also be associated with response, in the sense that a certain clinic might have a higher response probability. In this case, if we consider the association between treatment and response and ignore clinic, it is possible that we may either get a spurious association or we might get an association which is masked due to the fact that we have ignored clinic. Such variables are confounders, and controlling for confounders will be an important part of our analysis. Extending the concept of binary or binomial data, here is an example of multinomial data. Now you are all familiar with the multinomial probability mass function, which arises when we are trying to allocate n individuals to k fixed categories. So here the data has again three variables. One is center, one is treatment, and one is response. If I assume that the sampling design which has been used is multinomial sampling, then we have 8 into 2 categories. We may want to consider a regression problem for this kinds of data, and it will be necessary to extend the concept of regression to the case where we have a multinomial outcome. Let me provide you with another multinomial data set. So in this case, I have observed two variables. The first is the highest degree which one has studied. This has been categorized as less than high school or junior college, or bachelor or graduate. Along the columns, I have considered the variable religious beliefs. This could be fundamentalist, moderate, liberal. The source of this data is the General Social Survey of 1996 conducted by the National Opinion Research Center. This dataset has been studied by both Agresti and Faraway. Let me consider yet another example of multinomial data. Here, along the rows, we are considering income in dollars, which has been split into 4 categories. The first category considers those whose income is less than 15,000, the second between 15,000 to 25,000, the third between 25,000 to 40,000, and the fourth above 40,000. Along the columns, I am measuring job satisfaction, which I have categorized as very dissatisfied, a little dissatisfied, moderately satisfied, and very satisfied. Now, I have introduced you to 3 different kinds of multinomial data set, and you may have noticed that even though all of them arise from multinomial classifications, there is a subtle difference between the first table and the next 2. What is this difference? To explain this, I have to go into the concept of nominal versus ordinal. Categories are considered nominal when they have no natural ordering. Examples could be religion, nationality, types of residence, and so on. Such categories can arise in the social sciences, in econometrics, in biostatistics, and so on. Ordinal variables are those variables whose categories have an ordering, and in fact, the ordering should be a natural one. So examples are preference, education, smoking. It should be obvious to you now then that the variables which we have considered in the first table is a nominal one. We have considered clinic, and there is no natural ordering of clinic. The numbers 1, 2, 3, etc. I have chosen are arbitrary ones, and I might as well have reordered or chosen a different set of numbers. The categories are thus nominal categories. However, when I look at education, or when I look at preference, or even when I discretize income into income classes, the categories are now considered ordinal variables. Why is this important? Well, firstly, there is a measurement hierarchy which says that interval variables rank higher than ordinal variables, and these in turn rank higher than nominal variables. Interval variables? Well, interval variables mean that it is not only possible to order the categories, but the actual labeling of the category has a meaning, and in fact the ratio of the two measurements is also meaningful. The measurement hierarchy says that it is possible to use methods for nominal data on ordinal data, but not vice versa. In general, it is possible to use methods for any lower category on the higher category, but not vice versa. Now, I have said that it is valid to use these methods. That does not mean that it is recommended to use these methods. It just says that it is not invalid to do so. We can always benefit if we use extra methods for ordinal data which take into account the ordering of the categories. The reason is that we can now answer additional questions. For example, we could quantify something like the average preference, and we could also look at trends in preference. So, for example, in which direction does political belief change with change in schooling? Does it increase with schooling or does it decrease with schooling? Because there is an ordering of these categories, it is possible to raise and answer these extra questions. Nominal versus ordinal. I have already mentioned the distinction between ordinal and interval or ratio variables. In case of ordinal variables, we are able to order the categories, but the categories by themselves have no absolute meaning. In case of interval or ratio variables, the actual measurements are meaningful, and so is the ratio between the measurements. Now note that the same underlying concept could be measured in alternative ways, as either an interval or ratio variable, or as a nominal one, or as an ordinal one. So, for example, I could try and quantify education using the number of years of schooling, in which case I have used an interval or ratio variable. I could quantify it as private versus public, in which case I have used a nominal classification, or I could consider it as ordinal by categorizing it as primary, secondary, graduate, or postgraduate. The relevance of the definition depends on my problem and the question which I am hoping to answer. Changing gears, another type of variable which will constitute a major part of this paper are counts. Now, we have seen counts in the context of the Poisson process and the Poisson distribution. So we know that when we have a rare outcome which is being measured over time, for example, mutual intervals are non-overlapping and so on, we have a process which is called the Poisson process. And we also know that when we are observing events which occur over time or over space, the natural PMF in many cases is the Poisson PMF, which is given on this slide. So some examples of Poisson variables which have been made famous by R. The first is the number of species of turtle. This occurs in the Gala dataset in R, and it refers to the number of species of turtle on an island in the Galapagos Islands. The second is the number of seizures. So there is a famous dataset which looks at progabide and the number of seizures for the longitudinal datasets in R. A third could be the number of accidents, where we might be looking at the number of accidents of a particular type which occur daily in a specified region. This brings us to the concept that the natural metric to consider may not always be counts, but in some cases it might be rates. So we might wish to standardize the counts and look, for example, at the incidence rate of lung cancer, the mortality and morbidity rate, the fertility rate, the number of accidents per capita, the number of earthquakes per capita. So all this happens when we are comparing counts which arise in different geographical populations. So for example, mortality and morbidity of different countries, which would differ simply because the size of the countries are different and not due to the change in the intensity at which mortality and morbidity occurs. In this case, we want to nullify the effect of size, and we can do this by modeling the rate and not the actual count. There is also something called an over-dispersed count. Now you know that for the Poisson distribution we assume that the mean is always equal to the variance. But it is not necessary that whenever we have a count, the mean and the variance will always be the same. So the question arises, what we could do in such a situation? The answer is that we can fit something which is somewhat close to a Poisson regression, but which allows for the fact that variance of y is equal to some parameter phi e of y. By default, phi is assumed to be 1 and we have the Poisson distribution, but it is not necessary that it will always be so, and in fact we can see from the outcome that the estimate of phi given here, which has been mentioned as dispersion parameter for the Poisson family, has been estimated as 31.749, which is considerably different from 1, and hence we have a situation of something which can be referred to as over-dispersed counts. Now, as we do not know any ready-made PMF for counts which allow the mean to be different for the variance, this is one area which we will study further in this paper. So finally, a quick mention of the generalized linear model. I have mentioned several discrete data sets in this paper, but in fact, the regression methods which we will develop in this paper will be valid not only for the discrete data sets, but for a wide class of family of distributions which has been written to on the first line on this slide, called the one-parameter exponential family, allowing for a scale parameter theta. We shall define something called a linear predictor, which we shall refer to as eta, which sums up the effects of the covariates, and we shall also define something called a link function, which in turn will relate the expectation of the distribution to these covariates. But more on this later, and we will have several dedicated modules for the generalized linear model. In the second introductory module, I have provided you with an exposure to the kinds of data sets which we have handled in this paper. We have seen binomial data. We have seen that this data can be of various types. It can be extended to general categorical data. Categorical data again is not unique. It can be of many types. So for example, for a 2 by 2, that is a 2 variable classification, we could have ordinal variables, we could have nominal variables. We have also seen that we may have counts, and even for counts, whereas we have always assumed that a Poisson distribution will hold in the past, there are certain cases where the Poisson distribution is not immediately applicable, as in the case of over-dispersed counts. Finally, we have seen the motivation of a concept called the generalized linear model, and in subsequent modules we will see that this can be used as a tool to handle discrete data, and not only to handle discrete data, but to handle a large family of distributions, of which the linear model will be a special case. However, the methods will also be applicable for all the discrete kinds of data sets which we have seen in this module.